let's get started. So, recording has started. Yesterday, you realize that's out there on the internet, so whatever it is that you're saying.
No, it says this is Planet Sex Computer Broadcast.
Nice.
You needed a name, sorry.
I need a better name for my channel. It's just Mr. Planet Sex.
Yeah.
All right. Yesterday, we got into energy. We talked about energy in a general sense as being what? The ability to do stuff, or the ability to change things. And we talked about all these different kinds of energy, like electrical energy and electromagnetic and nuclear and all these things. But the one common thread that follows us through is the fact that we're making things different than they were before. That's the gist of energy. That's what energy is. That's what energy does. That's how we explain why things or how things change. Yesterday, at the end of the period, we started getting into the idea of mechanical energy. So we said that with mechanical energy, we're concerned about first bigger objects. We're not talking about atoms or molecules in this case. We're talking about bigger things like you and me and trucks and cars and airplanes and things like that. Okay? But in our discussion of those things, we're concerned with two factors. And what were the two things that we were concerned with when we're dealing with mechanical energy? Motion and position. All right? So we're concerned with where these objects are, especially in relation to other objects, and what they're doing, right? So where they are and what they're doing, and what kind of change or what kind of damage they can do because of those things. Good.
So position, there's like one ball at the bottom of the hill, one ball at the top, and then like motion would be like the ball on the top starts moving.
How fast is that ball going at that point in time? Yeah. So we'll talk. We'll talk.
Like do examples.
Yeah. So yesterday, Sam, we talked about kinetic energy, right?
Yeah.
So we said that kinetic energy is energy of motion. That because something is moving, it has the ability to cause damage or to change things from what they were, right? For example, and I'll use this example to keep up with it. If I roll a bowling ball and it's rolling across the table and it rolls over my fingers, okay, it has the ability to hurt my fingers because of the fact that it's moving. Not necessarily because of where it's located in any specific, and we'll talk about that in just a second, but in that case, because of the fact that it's moving, it has the ability to hurt my fingers. Okay?
And if it wasn't moving,
it
wouldn't hurt your fingers.
Right, it wouldn't hurt my fingers, right? We said that kinetic energy depends on two things, right? And they are?
Mass and velocity.
Mass and velocity, or mass and speed. Because I think we talked about at the end of the period yesterday that regardless of what direction we're going, that doesn't affect how much damage we can do. That energy is a scalar quantity, so even if in this equation, if we did somehow, put a negative number in there for the velocity, it all comes out anyway because we're squaring it and blah, blah, blah. Okay? And then I think we left off here yesterday, right? Talking about the different effects, okay? That mass and energy, kinetic energy, have a direct relationship. That if I double the mass of the object, it does twice as much damage, or it could do twice as much damage, right? A heavy car versus a light car going at the same speed. But when we look at the formula, what are we doing mathematically to the velocity in that formula? You're squaring it, right? So that velocity or speed and kinetic energy have a quadratic relationship. That if I go twice as fast, how much energy do I end up with? 4 times as much. If I go 5 times as fast, 25 times the amount of kinetic energy, because we're squaring that value. Okay? Good there? Okay. Did we get into potential energy at all yesterday? I can't remember. Okay. All right. Let's talk about potential energy. I'm assuming that most of you have at least heard of potential energy somewhere before. And there's always one definition that comes up when we talk about what potential energy is, as opposed to what's written there. What do we kind of talk about as far as potential energy is concerned?
It's like gravity.
Gravity does have a definitely part to play in it, okay? I heard somebody kind of start saying it like that. You said potential energy is what kind of energy? Stored energy, okay? I don't like that definition. because I don't think it's very descriptive as far as what potential energy actually is. So, with that being said, let's try and change your thinking a little bit. Whereas kinetic energy is energy of motion. Because something is moving, it has the ability to do damage. And Sam, we just kind of talked about the idea with the bowling ball, right? If that bowling ball isn't rolling, it doesn't do any damage to my fingers. Okay? However, because of where it's located, it could possibly hurt my fingers or my toes, right? See, if I have that bowling ball sitting still on the table, sorry, I know you're great.
No.
So if it's sitting still on the table versus sitting still on the ground, does it have potential to do damage in one location versus another location? Well, it's sitting still, so it's not going to hurt anything because it's moving, right? But what could it do off of the table that it can't do off of the floor? If it falls off the table, could it do damage then? Yeah. So because of where it's located, it could possibly hurt my foot or something like that. Right? The object has that ability to quote-unquote do damage or cause things to change because of where it is. And just sort of wrapping up, we sometimes it gets referred to as stored energy, but I like the idea of energy of position way better because I think it's a much better description as far as what potential energy is. Because of where this object is, it could potentially cause things to change.
Can you measure potential energy? Because like if the bowling ball's just sitting there, what would you just measure that?
Now remember, it's potential energy, right?
Yeah.
So it has the potential to cause damage,
Yeah.
not that it necessarily will. Okay? Like the bowling ball sitting up on the table is only going to cause damage if what actually starts happening.
Okay.
If it starts moving and falls off the table, right? So the potential to cause damage is there, right? As opposed to what is it actually doing. So like we said, we're concerned about two things: where it is and what it's doing. This takes care of the where it is part. What might happen because of where it is. Okay? And Caroline, this object that's moving, it's really only causing damage if it runs into something else, right? But it still has energy regardless of if it runs into my foot or not.
Yeah.
Does that make sense? Good.
Do we know if the potential energy, I don't know what I'm trying to say, will happen? What if?
No.
No.
That sort of
this is
depends
an
on what happens.
estimate,
Yeah.
this
This is more, like I said, it's potential.
Okay.
So there are two kinds of potential energy that we talk about. First, we're going to talk about gravitational potential energy, okay, or PE sub G. Okay. If generally potential energy is energy of location or energy of position, what do you think gravitational potential energy is going to be associated with? How high something is, or its potential energy relative to its location to the ground. Technically, it's relative to its location from a source of gravity. Generally, that source of gravity that we deal with is what? The Earth. Okay? But technically, the moon could cause potential gravitational energy. Technically, you could cause potential gravitational energy because you are a source of gravity. Generally, we refer to it as the ground, okay? Or generally refer to it as the Earth. Okay? The amount of potential energy an object has depends on three things. It depends on that object's mass, that's the m in that formula. It depends on g, and we thought g is what?
Gravity.
Specifically, what about gravity? Not the force of gravity, the acceleration of gravity, right? Which we know now is what value? Around 10, 9.8, right? And then h, what do you think h is going to stand for? Height. Okay? Now, the height parts can get a little confusing. Okay? Gravitational potential energy is a very relative sort of thing. Okay? If we have the bowling ball sitting here on the ground in this room, if you asked all of us, could that bowling ball potentially do any damage, what would all of us probably answer?
Yeah. No.
If it's sitting on the ground in this room, right? We'd all probably say no. But what about if you ask somebody at the bottom of the steps over there? They would say, yeah, it probably has the potential to do some damage, right? So when we talk about the height in this formula, the H value, that's a very relative term. And you have to sort of make sure everybody's on the same page. It gets back to the idea of frame of reference that we talked about, okay? So that's going to generally be, like I said, that's going to be more of a relative kind of term. Now, most situations, it's going to be pretty obvious as far as where we are going to say this is the ground. But just be aware that that value might change depending on who you ask. Okay? Go ahead.
The equation up there, it says y.
Yeah. In this, the y being the y-axis, so it's still dealing with a height kind of thing. Depending on what book you read, where you look at it. I use this for physics class because in physics class we deal a lot with two dimensions. We deal a lot with the x-axis and the y-axis, so to kind of keep that straight. Same idea. It's still a height value, which is a different way to call it. Good on potential gravitational energy. We said that our mechanical energy depends on three things: kinetic, gravitational potential, and elastic potential. If you notice up here at the top, it says PEG as well. In the heading, that should say PEE, but I think on your notes it actually does. Is that correct? Okay. Yeah, so elastic potential energy. Potential energy that results from something being stretched or compressed. If I take these rubber bands, right, and I stretch them out, what are they going to try and do naturally? Go back to the position, the original condition that they were in. If I set up something properly, could I use the rubber bands going back to their original position to do something for me? To make things different, right? I could shoot things across the room. I could flick somebody and make it hurt their arm, whatever it is. Okay? The idea that things want to continue or stay in their current state and get back to that current state, if we change them from it, we can use it to do stuff, to make things different. And that's where elastic potential energy comes in. Okay? The bow or the string on this bow and arrow, the spring in this car. If I wind the spring up and crunch it all down real small, as it stretches back out to get back to its original position, we use it to turn the gears inside the car, or however the spring is set up inside of it. Go ahead.
In like the arrow example,
yep.
What has the potential energy? Is it the string or the arrow?
Technically the string. The arrow, the energy comes from the stretching of the spring, or the string, okay? So, Caroline, when we look at how much potential or elastic energy something has, it depends on two things. It depends on the material itself, okay? This rubber band, one rubber band, in the big picture, really can't do that much damage, even if I stretch it like that, okay? It could break as well, okay? But if we talk about, the potential gravity or the potential energy that comes from stretching, like the springs on your bed.
Yeah.
Okay? Those are really, if you crunch those down, they're going to spring back really hard. So it depends on the material, but it also depends on how far I stretch it. So in this case, because it depends on how far I stretch it, the energy, the elastic potential energy in that picture of the bow and arrow is coming from the fact that we're stretching the string. Does that make sense?
Yeah.
We make use of that fact on the arrow, and that's actually what we're going to talk about next. Okay. All right, are we good with the different types of mechanical energy? Kinetic, gravitational potential, elastic potential. All right, one more term that we introduce in this section here, and that term is work. Okay. Work is one of those terms that if you don't keep it straight in what its definition is, you may answer questions incorrectly because of the fact that work has a specific definition when we're dealing with energy. Okay?
Is it extinction?
Could be. Okay. When we talk about our definition of work, we define work as the transfer of energy between objects. In order for work to be done, the energy of an object has to change. If work is a transfer of energy between objects,
So
say again.
work is only done when
We haven't gotten to that part yet. The second bullet point, the open square, is more of a clarification of what the first bullet point means. Okay. So Caroline, going back to our example from before. Okay. The string does work on the arrow because what happens to the arrow as the string is pushing on it? It goes faster, right? So it's gaining kinetic energy as the string itself is losing elastic potential energy. It's not stretched as far. Does that make sense? All right. If energy is going to change, we talked about three things, three kinds of energy that make up mechanical energy. What's the first kind of mechanical energy that we talked about? Kinetic. If the kinetic energy of something is going to change, what has to happen to it? Not so much that it has to move. If the kinetic energy is going to change, it can change mass, but if it changes mass, it's more specifically, Allison, what kind of velocity change? It has to either speed up or slow down. Either one of those is a change in kinetic energy. Okay? Going back to the last chapter that we talked about, what has to be true if something is speeding up or slowing down? What do we have to apply to it? A force. Okay? In order for something to change its gravitational potential energy, what has to happen to it? It has to either fall down or go up, right? It has to change its height. If we're going to move something up or down, right, what do we have to apply to that object? A force, right? For something to change its elastic potential energy, we have to do what to it? Stretch it out, stretch or compress it. If we're going to stretch or compress it, what are we going to have to do to it? We're going to have to apply a what? A force, right? So, in order for work to be done, there seems to be a common theme here. What do we need in order to have work? We got to have force, okay? So, work is only done if we apply a force, and then that object's motion changes because of the force we've applied. And we'll get some examples of that here in just a second. 23 is my number. So, the amount of work done in a situation depends on the force that we apply and then the distance that object moves, F times D. Okay. Good there? All right, let's talk about some conceptual situations. First situation. A guy throwing a baseball. Kurt Schilling. So, is this work by our physics definition of work? Okay, so two ways we can look at it. Okay, so the correct answer first, yes, this is work. So underneath your picture on your notes, right, you can circle yes. Okay? So Allison, let's look at it from an energy standpoint first. We said in order for work to be done, what has to happen to the energy of an object?
Change.
It has to change. Does the energy of the baseball change because of what he's doing to it?
Yeah.
Yeah, specifically what happens to it? It speeds up, right? So that means that that ball has more kinetic energy because of the applied force. Does that make sense? Allison, if we also look at it from the definition, does that guy apply a force to the ball? Does it move because of his force? So that also fits our definition of work as well. Okay?
Why is it?
Because what's happening to the ball because of what he's doing to it?
Oh,
It's moving faster, right? Go ahead.
like you try to move something, but it doesn't move.
Hold on 1 second. Actually, a couple of seconds. That's not the next picture. It's the following picture. So, second picture. Is this work?
Yeah.
Yes. Let's talk about it from an energy standpoint first. By the girl doing what she's doing to the box, what happens to the box?
potential energy also.
Well, in this case, it is moving, but Nick, where is she moving it to? Up. So what's happening to its potential gravitational?
It's going up.
It's going up, right? So yes, this is work. That crate has more potential or gravitational potential energy because of what she's doing to it. Also, Nick, we can say again. I guess you. Well, in that case, okay. In that case, there is some work being done, and in that case, Kennedy, the work isn't being done by the girl. It would be done by gravity in that case. Now, in this case, let's just, Kennedy, that's actually a good question, Kennedy, okay? If we assume that the box is moving up in this picture, the girl has done work on the box because she has increased its gravitational potential energy. If the box was falling downward, we would say that work is being done, but it's being done by gravity in that case because it's going faster because of what gravity's doing to it. So that would be an increase in kinetic energy. Okay? But in either case, it's still work. Okay? Good there? Okay. Miriam, here's your question. Okay? And this is something I'm sure a lot of you encounter at home because I know a lot of you are like into like marble sculpting, you know? So yeah, finally I've gotten something that you guys can relate to. I know. So.
And we're bald.
Yes. So. But apparently, once again, no dollies or carts exist in this world, and all we can do is just tie strings around things and try and pull them to where they need to go. Yeah, I mean, see another way that it relates.
It's a movie or saying.
So, in this case, Miriam, okay, that guy pulls really, really hard on the block of granite, but it doesn't go anywhere. Okay, is that work?
No.
Okay.
But yes, because of the transfer.
Okay. So, is he, quote unquote, working hard?
Yes.
Yes. But, based on our physics definition of work, is that work?
No.
Is the energy of the block changing because of what he's doing to it?
No.
Does it go faster or slower?
No.
No. Does it go higher or lower?
No.
No. He is still applying a force. Okay? But, Allison, we said in order for their work to be done, two things have to be true, right? He has to apply a force, but what else has to happen? Look at the formula. Down at the bottom of the work slide. Top right. FD, where D is distance, right? Is he applying a force? Is there any distance, though? There is not. Right, there has to be a force applied, and there also has to be a distance moved. And if that's the case, there's going to be a change in energy. Okay? So two ways we can look at this. One, if we look at its energy, it isn't speeding up or slowing down, so there's no change in kinetic energy. It's not going higher or lower, so there's no change in gravitational potential energy. So no work. Also, there's a force being applied, but there is no distance. So if you have force with no distance, it's not work. Does that make sense?
Yeah.
So two things underneath the marble guy. But in order for there to work, so Miriam, if you go back to the top right of that side of the page, the top right slide, the very bottom thing says that work is equal to F times D, right? What's D in this case? What's the distance that this object moves? So what's the work? Does that make sense?
So, like, isn't it asking if there's a force?
Yeah, it's asking for force.
No. The amount of work that we do on an object is equal to the force we apply times the distance that we move it. Both of those things are required for there to be work done. So in this case, you are applying a force, but it's not moving because of your force. And if that's the case, you're not doing work on it. Okay? All right. Here's another situation that I'm sure a lot of you are familiar with. Running away from big boulders. Okay? And I'm going to assume here, because of the fact that you're all sitting here in class now, that you have successfully outrun these boulders. Okay? So, eventually that boulder stops. Is work being done on the boulder as it's coming to a stop? Yes. Okay. Does its energy change because of what friction is doing to it? Yes. Technically, what does friction do to things? It slows it down. That's a change in energy. But what kind of a change in energy is it? It's a negative change in energy. So, Miriam, what kind of work would we say that friction is doing in this case?
Negative work.
It's doing negative work. Okay? It's still a change in energy, but it's a negative change in energy. Waiting for somebody to ask me this question, but nobody asks it now.
Well, if you have a negative potential, it isn't gravity.
Yeah, gravity isn't enough.
Anthony, isn't gravity doing negative work because what is gravity doing to the height of that object? I'll save that question for Friday.
Not even one single.
Wow.
All right. Real quick. Calendar. Calendar has been updated. These problems that show up on Tuesday relate to what we talked about in class today. Anthony, great question. We'll save it for Friday.
Let's go.